Was bumbling around the place and I came across this at a shop called Daiso, which is like a Poundland or a dollar store or whatever here in Japan, but they do have some more expensive stuff. Usually it prints on the pack. This one was $3. It's a USB charger, 2.4 amp for your phone. Now there's two types of this. This one is for Android and it's a black version. The white version is for Apple devices, so they'll just put different voltage dividers in the on the data lines there to tell the Apple device or the Android device how much current it can draw. So if you've got an Android, make sure you get the black one so that your phone will charge at the full rate. And also if you've got an Apple device, make sure you get the white one. And that will make sure that your Apple device charges at the full rate. So yeah, these are 300 yen, and I thought if people are coming over to Japan, they might end up looking for one of these things, and I'll review this one because it's easy to get pretty much anywhere in Japan, and we'll see if it's any good. 2.4 amp is always a good amount of current to charge your devices relatively quickly. So yeah, let's rip this thing open and we'll give it some tests. This one here is good for AC 100 to 240 volt, 50-60 hertz, and the output is 5 volt at 2.4 amp maximum. So you can use this with an adapter to plug it into your Australia or European or English or whatever outlets, and it will work at the higher voltage. So it's a universal voltage, but it's got the Japanese / American style 2-pin plug. Now to get this open, I'm going to have to give it a little bit of a clip, and we'll tear it like that. And there is our device. Got the plastic wrap on there, which I love to tear off. Oh yeah. That's what we get. There's no included USB cable, but they can be purchased for $1 each as well. I got one here. This is from another dollar store, but 2 amp rated, 50 centimeters for $1. So yeah, pick up one of these, pick up the USB cable, and you're set. So this one here actually has Android written on the front. I'll hold that up. Maybe, yeah, there you go. And the Apple one has Apple on the front there. The connector on the back just clicks out like that. So that's real convenient. Fold it away when it's in your bag so it doesn't get bent. And it's got the relevant gear on the back there. Double insulated, indoor use only. It draws 0.3 amp from the mains. 100 to 240 volts, usual stuff that we just read before, and made in China. So let's hook this up to a load. I've got a 2 amp resistive load, just a USB tester, and we'll hook up to the oscilloscope and see how much noise and whatnot and the actual voltage output that this puts out. See if it puts out 5 or maybe a little bit more, because the USB spec does allow up to 5.25 volts, and if you're running something like a Raspberry Pi or high power devices, sometimes they'll bump it up just a little bit above 5 volts so that they'll take into account any voltage drop on your USB cable. So let's plug this in and see how it performs. So we're all hooked up here, 100 volts into our power supply. We got the load here, it's just a resistive load. We can switch between 1 and 2 amp, and then the wires coming around to our voltmeter. I like using resistive loads, especially when testing for noise, how much electrical noise is coming out of these power supplies, because if you use a MOSFET style, that's fine for just checking voltages and applying a load to load test. But if you're looking for how much noise is coming out of this thing, those MOSFET-based ones, the switching on and off of that MOSFET can skew your readings. So the resistive load is basically as pure a load as you're going to get, and that won't affect your readings on the oscilloscope, which we'll check out later. But for now, we'll see how much voltage this thing's got, how much it's going to kick out. So I'll plug it in. And at 1 amp, we're getting 4.9 volts. If I flick that to 2 amp, still 4.9 volts. So it's just a shade under 5 volts, but it's close enough that it's basically 4.95 volts. That rounds up pretty close to 5 volts. So that's all right. I'll give that a thumbs up. Would be nice to see a little bit more voltage, like 5.2 volts, just to take into account that voltage drop on the USB cables. But yeah, I'll give it 2 thumbs up if it had a little bit more voltage, but still, that's perfectly usable. So let's see what it says using a USB cable. Now this is the 50 centimeter long, 2 amp, so it's a decent current. We're not going to overload the current according to its specifications. And being 50 centimeters and whatnot, it's a good representation of what an average cable would be. I mean, we're going to be testing this cable a little bit in this test, but it's kind of a real world estimate of what you would expect to happen. So let's plug that in. And what are we getting? 4.65 volts at 2 amps. 4.76 volts at 1 amp. So yeah, you can see when I increase the current, we decrease the voltage, because that's the voltage drop over the cable. That's just Ohm's law. So that's still not terrible. It would be nice, like I said, to see a little bit more voltage, but it's perfectly usable in any case. Yeah, Raspberry Pi might complain a little bit, but for charging a phone, that's not a problem. Alright, well, I'll hook up the oscilloscope and we'll see how much noise this thing kicks out. Make sure that's within tolerable standards, and then we might crack the thing open and have a quick look inside. So we're hooked up to the scope here, feeding straight in, and this is what we get on the screen. I've zoomed in quite a bit, so it does look a bit worse than what it actually is. The frequency is about 44 kilohertz, 45 kilohertz. That's just the switching frequency of the switch mode power supply inside the charger. The RMS value there is 70 millivolts, which isn't so bad. The peak to peak, however, is 520 millivolts. That's half a volt. But still, that's not that bad, because the transients are so small that, you know, with the resistance of the USB cable and the regulators and stuff inside your phone, those transients will get smoothed out pretty quick. It's the RMS value that we're more worried about, and 70 millivolts ain't bad for a $3 charger. If we zoom the scope out a bit, we can see more of the waveform. It looks messy, but it is under 250 millivolts in general. There's a few spikes there that go up a bit higher, but they're only very spurious, so they're not going to cause much of a problem. So 250 millivolts in general. The RMS of that value, when we zoom it out, is coming to 83 millivolts. That's still not too bad at all. So that's I don't see that causing a problem with any smartphones really at all. I've tried it on mine and it works fine. Doesn't jam up the screen like some really cheap, crappy chargers will do. Time to crack this baby open. So it seems like it's just glued shut. So a bit of a twist and a shake and it's come undone. Got our connections, which flick out here, and it looks like they've got little spring terminals which then connect down to the solder pads here. And because they're a spring terminal, even if the solder was to migrate, under pressure it tends to do that, the spring pressure is going to keep the connection there. So that's no problems there at all. Especially not for the 0.3 amp that we're going to be pulling through it. Alright, so it looks like we've got some good isolation, which is always good to see. Big open space straight through the middle, separating the high voltage and low voltage. Some isolation gaps there. So that's right where the USB port is, so that's really nice to see. And also, looks like with the rectifier here, we're separating the AC from the DC side of the circuit, even on the high voltage side. So yeah, that's not a problem at all. That's a thumbs up on the isolation for sure. This here is our bridge rectifier, full bridge rectifier. Coming in through a, looks like we've just got a 0 ohm resistor there as a jumper, a few discretes, and on the other side we've got the main controller chip. That is it's a Win Semi brand, a WS2597, just a standard kind of switch mode control chip there. There's our transformer, the usual sort of thing for a switch mode, and our feedback capacitor, bootstrap capacitor, and it looks like there is no opto coupler. Often they have an opto coupler to provide feedback, but this one doesn't have anything like that. So yeah, well, there you go. But after the transformer, we've got our output here. That comes into this chip. This chip is actually an FT8370, and it's a synchronous rectifier. This is doing the same job as this, but there's a difference in that this is an active component. It doesn't just have diodes inside. It's got actual MOSFETs, and it switches so that you can increase the efficiency, because when a MOSFET turns on, it acts like a diode, but because you forced it on with the gate, that means that the forward voltage drop is only less than 0.3 volts. It's like 0.03 volts, or yeah, really, really small. Whereas a silicon rectifier it's got like a 0.7 volt generally voltage drop. And if in a full bridge rectifier, because you've got two diodes in circuit at all times, you're dropping 1.4 volts. Now at mains voltage, that's not such a big deal, but over here we can reduce heat and we can reduce the size of our components, and we're wasting less of our 5 volts through heat. So that's a nice addition there. We're coming over here, got some nice thick traces with the usual, they expose some of the solder resist, so they can get some solder bridges there to increase the thickness. And then just, well, if you can see them, just at my fingers there, we've got some unpopulated pads. Now they'll be using the same circuit board in the Apple and the Android version. In the Apple version, they'll put some resistors there, and that connects to the data pins so that the iPhone can read those resistors and then determine how much power that the power supply can put out, and then it will charge at an appropriate rate. If you used the Android version, this one, on the Apple, it probably won't work. It will work, but it won't work at the full rate because the Apple won't see those resistors, and then won't charge at the full rate because it will assume that the charger is a low power charger. On the other side here, we got the output capacitors. We got 1,470 microfarad of output capacitance, which is not too bad at all. We could probably get rid of some of that noise if we had an inductor there, but inductors are expensive, and they haven't put one in because, hey, it's only a $3 part. $3 a unit. So, yeah, the internal construction looks quite good. Nice isolation there, synchronous rectifiers, a proper controller chip. So, yeah, I'm quite happy with that. I mean, the brand of the capacitors, Chongnex. Usual cheapest bottom of the barrel quality there, but the output capacitors apparently are low ESR. So yeah, I mean, at face value, it's not bad at all. So if you need a battery charger or a phone charger, head over to Daiso and grab one of these, because they turn out to be not too bad at all. So I might glue this back together and put it to use. Alright, that's all we got for this video. Don't forget, we got that Patreon. Keep watching the videos. We'll see you next time.